Hi box modders. So this video was going to be just about battery sag, and as I went through and made this fancy pants PowerPoint, I found myself including a lot more than just battery sag. So this is going to be an analysis, a voltage, current, resistance, power analysis of several different mod configurations. And what I'm hoping to do here is explain how a mod works, how every part of it comes together to make a functioning vaporizer. So we're going to start out with the ideal mod, the imaginary mod. And this is I'm just using a Samsung 25R for reference. I really like these cells. You can apply whatever you want, and you're going to see what you'll need to do this on your own very soon. So we have the cell, we have some wires, we have, this represents the atomizer, 0.1. You could do this with whatever resistance you want. I don't care. I used 0.1. It makes the math easy, at least for now. And then a fire switch. It doesn't have a MOSFET. Oh my god, what am I going to do without a MOSFET? I'm not going to do fucking anything except fire this mod. So, yeah. Next. So we apply 4.2 volts, and in the imaginary mod we get 4.2 volts to the atomizer. It doesn't really work that way. But this is how a lot of people think it works. And that's what we're going to try to do today. I'm going to show you that it doesn't really work that way. The first thing we have to understand is this cell is represented by a source and a resistance, and that's what we have here. This is our practical mod. I pulled this from the datasheet for the Samsung 25R. Typical was like 13.2 milliohms. I just rounded it to 13.2. If you don't agree with me, that's fine. This was from the Samsung 25R spec sheet. You could put whatever value you want here. The math works out the same. I used one that seems to represent how the actual cell is set up. My other values, also, if you want to argue with me about them, go ahead, I don't care. 5 milliohms for the wire, 15 milliohms for the switch. You guys out there that want to argue that, really don't care. And 10 milliohms for the solder joints connection, compression connection of the center pin on the 510, threads on the 510. I'm being generous, I'd say, with all these values. Your values may be higher, they may be lower. It doesn't really matter. You can apply all of this on your own because I'm going to show you how. So when we apply 4.2 volts, which is, remember this together represents the battery, we end up with 2.937 volts at the atomizer. How is that possible? How did we lose all that voltage along the way? Well, let's see. First off, our total resistance, and this is done simply by calculating everything in the circuit. So we add 0.1 to 10 milliohms. And by the way, 0.1 ohms, that's 100 milliohms. I should have done it all in milliohms, but I didn't. Because we talk about these in decimals normally. So 100 milliohms plus 10 milliohms plus 15 milliohms plus 5 milliohms. So this is 0.01, this is 0.015, this is 0.005, and this is 0.013. We add that up, we get 0.143 ohms. Total system resistance. Now, all of these are in series with each other. How can I tell? Because I trace my mouse cursor across. We have one, we have this, we have this, we have this, we have this. They're all in one big line. They're all in one big line together. That is series. So series resistances add, and in a series system you can only have one current because there is only one path. That should be pretty self-explanatory. So one path, one current, we take the total source voltage on a fully charged cell. We divide it by the total resistance of the system, because in Ohm's law we know that I equals V over R, and we get 29.37 amps. Good enough, right? Now let's go further. So this is the full analysis, and I'm going to walk you through this entire process. So to figure out the voltage at any given point, once we establish our total resistance and we establish our total current, we use Ohm's law, V equals IR, pretty basic stuff, and we get 29.37 times 0.1 equals 2.937, which is what we got here. Drop across the connector is about 0.29 volts, drop across the switch is 0.44 volts, and drop across the wire is 0.14 volts, or 0.15-ish. These are all values you can change. You can improve all these values by, say, using larger wire, or using a MOSFET, or whatever you think the best possible switching device is. And here you can improve your solder joints. You can use a fancy pants hybrid connection, I suppose. There's a lot of clever ways you can improve all of these. Battery sag, though, 0.3818. You cannot do anything about that if you are just using one Samsung 25R. You can't. That's it. That is the price you pay for using one cell. If you decide to, and I'm going to show you what the change is when you use two cells, you can use two cells in parallel. You could use a LiPo, and your run-of-the-mill high drain LiPo for RC applications is about half that, closer to 0.006 or 6 milliohms. So, and that's not even a high-end one. If you get an expensive LiPo pack, say like a Max Amps, like Sajid and his guys like, you will probably get even lower than that. Lower internal resistance equals lower battery sag, and I'm going to show you that coming up. So we've got that covered. Battery sag, got it. Now I want to talk about wattage. So we have 86.26 watts to the atomizer, and that is obviously calculated making assumptions about the internal resistance. So give or take a few tenths of a volt here, give or take a few watts, maybe even 10 or 20 watts here in real life. So that's what we get there. What do we lose? Because every voltage drop has a corresponding power loss. I squared R is one of the, and if you look at the Ohm's law wheel, you will see that I squared R is one of the power calculations. So we take the current, and it's an easy one for us because we have the total current and we have whatever resistances we want to add up. So this is watts lost in the mod. Notice I did not use the battery because we can't do anything about the battery. We're going to say that it's a tube mod, it's a single cell mod, that's all we can do. So I didn't use that in the calculation. If you want to, you can. You simply add the 13 milliohms to the 30 milliohms that are already here. So anyway, watts lost in the mod, that's the wire, switch, and connector, 25.88 watts, and that is considerable. There are mods that don't even put out 20 watts. So what can we do about that? Once again, you can improve your resistances across here, but there are other ways. And I'm going to show you soon. But first, I want to show you, back on the topic of battery sag, how we can improve sag. And that's by, of course, paralleling cells. Practical mod, paralleled. And this is, I'm just going to, that looks better. So we have two of these in parallel. The equivalent circuit is a single cell with half the resistance. Resistances in series add. Resistances in parallel, if they are the same, are 1 over the number of resistances. So 1 over 2 resistances, that's 1/2, 6.5 milliohms. I didn't run through every single value here this time because the change isn't that significant. We have 30.77 amps as opposed to 29.37. The current doesn't change a lot because the resistance doesn't change a lot. The only change in the resistance is inside the cell. So let's look at what it does to the battery sag. Instead of dropping 0.38 right here, it drops 0.2 volts. So we have recovered a lot. We have recovered almost half of our battery sag by adding another cell. And why is it not exactly half? Well, it's not exactly half because we have increased the current. We've increased the current. You notice we have increased the voltage to the atomizer, not by a lot, but by an amount that caused a noticeable increase. We went from 86 watts rather to 94 watts, which is probably a noticeable difference. That's why they say parallel boxes hit harder than tube mods. That's one of the reasons. All of this is another big reason. These values are much larger in tube mods, whether you want to believe it or not, guys. And if you don't believe me, then go get a high amp resistance tester and check it out for yourself. So that's that. Watts lost in the mod. We've increased the amount of current lost in the mod because we have increased the current. Mod resistance stays the same, so our wattage loss in the mod must increase. It doesn't increase by a lot, by about 3 watts, really 2 and change. So not a lot, but we've increased the wattage out, and we have significantly reduced battery sag. So number one thing you can do to lessen battery sag is to add cells in parallel. If you want to stick to a certain cell type, just start throwing more of them in parallel, and all else aside, that's going to help. Now there's a diminishing return on your investment as you add cells. One, ideally you'll reduce by half. Practically, you see we don't get quite half. So let's say we add 2 more cells, and this will go down to 0.1. Well, that's half, but it's only recovering 0.1 volts. And how much difference does that really make when we've had to add the space of 2 extra cells? We have to add more conductors, more contact points, more losses, and I didn't even account for contact losses in this model. You can roll that into the switch or the wire or the connector or whatever. This is all just for representation. So we can only recover so much before it's almost infinitesimal. It's not even noticeable, the recovery. And there was actually a CCI video. I don't know who did it, but he went through and actually showed this. He showed this in his quad parallel mod. He did it on 4 cells. I think he was at 0.05. He did it at 4 cells. He did it at 3 cells. He did it at 2 cells. I think he did it at 1 cell. And he showed the voltage at the atomizer each time. And so that was a real good video. That was a nice practical demonstration. And I'm really just showing you the math behind it. For those guys who have to see the math, I have to see the math. I'm familiar enough with it that I know it, but I want to show it to you guys so you can see it. Okay, let's move on. Oh, let me, okay. Did I do that one? Yeah, okay, we're good. So series. Let's talk, so we're kind of done with battery sag now. So if you're only interested in battery sag, you can pretty much kill it at this point. We're going to move on and talk about the analysis of a series mod from volts, current, watts, all that stuff, volts, amps, watts. So we have two cells in series. We know in series voltage adds. We know in series resistances add. So equivalent circuit, 8.4 volts, 26 milliohms. I didn't write out on all the voltages here. I put them down here. Okay. And I changed the atomizer value. If you guys read my series versus parallel right up, you'll see that the atomizer, the watt equivalent atomizer build, is going to be a function of the square of the number of cells you have. So you have 2 cells squared 0.4. We're going to see that again later. So watt equivalent, if you're just shooting for, hey, I always use parallel mods and I want to use a series mod, what do? If you normally run at 0.1, you start out at 0.4 and work your way around. That's just a guideline. Mathematically, in an ideal condition, it works out perfectly. In the real world, I'm going to show you how different, it's a little different. It can be different. Total resistance, so we have 0.4 plus internal resistance plus mod resistance is 0.456. Our current, same calculation, but we get 18.42 amps. Why? Because we have a higher resistance, we have a higher voltage, we have a much higher resistance, yet we only have double our voltage. Our current is going to drop. Atomizer, volts to the atomizer, 0.737, or 7.37. Now I want to show you the difference here. We're losing just over a volt from the source. Now I want to show you the parallel mod, where we're losing just over a volt from the source. It's actually 1.1 versus this, which is 1.03-ish, rounded. So we're losing, from the source, we're actually losing less voltage from full than we did in a parallel mod. And I want you to think about that for a second. One, we have less voltage to work with, and we're losing more of it from right off the top than we do in a series mod. Now, why is that? Well, it's not because of battery sag, because you see our battery sag is greater. It's more than double it than it was in our parallel mod. So we have so much battery sag. Where are we making up the loss? Well, we're making it up in the mod. We do that because we have less drop. We have 0.09 volts, 0.27 volts, 0.18 volts, versus, we're going to have to go up to here. I didn't do the math here, but the current's not that much higher, so it's not going to be that different. 0.14, 0.44, 0.29. It's because the current is almost double what it is here, so the values are almost double. That's why when it's here, the values are almost half, because the current's almost half. We regain a lot of voltage by dropping the current. And this goes to my next big point. You regain much more of your available voltage by dropping the current than you do by dropping the resistance. Why is that? Not so much the voltage, but the power. You're going to, and I'm going to show you this here. You can actually recover the same amount of voltage by reducing the resistance. But the power is where it really starts to show. So we have the same mod resistance, and we have current that's less, considerably less. It's the square of the current, though. So any change you make, any reduction you make in the resistance is just a function of the resistance. Any reduction you make in the current is a square of the current. So you're getting an exponential gain on your performance by dropping the current. And that's why it is much more effective if you want more watts to get to your atomizer. If you want to improve your performance, relatively speaking, a series mod is going to be easier than just making a series mod is going to be easier than improving a parallel mod. Take it for what that's worth. 10 watts lost. Enough rambling. 10 watts lost in the mod. So we have now 135, almost 136 watts to the atomizer. Before, in our parallel mod, we had 94.6. So in a watt equivalent, finger quotes, build, we actually have about 40 watts more, which is pretty good. That's a big difference. You may not have even built your atomizer to accommodate that. Okay, so what do we do if we have 3 in series? Let's go for 3 in series. Let's see what happens. So as we go through, this is our triple series, 12.6 volts. I skipped all the drama and the suspense. 12.6 volts, 13 plus 13 plus 13, 39 milliohms. Everything else is the same. We end up with a 0.9 ohm atomizer, guys. So why 0.9? Because we have 1, 2, 3 squared 0.9. All right. And if you had 4, it would be 1, 2, 3, 4 squared 16. So that would be 1.6 ohms. Sticking with me? Good. And so on and so forth. Okay, so that's with 0.1 as the multiplier. 0.1 being the base resistance. Okay, 0.969, so that's 0.039 plus 0.9 plus 0.030. 13 amps of current, so now we've dropped our current even lower. Atomizer voltage 11.7. Now we're losing less than a volt from our battery to our atomizer. Less than a volt, folks. And look at our battery sag. Our battery sag isn't much worse. Now you might be asking me, why did it go from 0.2 to 0.47 to 0.5? Well, let's look at what it really did here. Is it went from 0.38. This is our single cell to 2 cells to 3 cells. And the reason we're seeing this drop off, it's still a curve. It's not a line. It's definitely a curve. We go from 0.38 to 0.47. Because that's a jump, that is a jump, to 0.507, 0.51. That's less of a jump. Why is our battery sagging more but not in a linear fashion? It's not sagging as much as you might think it would. It's because of our current. We're dropping the current, we're dropping the current, we're dropping the current every time we add these cells in series. Less current, less relative loss. So our battery sag increases, we know it will, but maybe we thought it would increase by more than that. And it won't because of the reduced current. So V equals IR, we have 11.7, and our wattage to our atomizer, this is, you can do this I squared R, you can do this V squared divided by R, anything on the wheel, the Ohm's law wheel will work. 152 watts. Now we've gone all the way from 94 watts to 152 watts. That's no joke. That's a 60-watt gain, nearly. Watts lost in the mod. Now we're down to 13 amps squared times 0.030. 5 watts. 5 measly watts lost in the mod. You wouldn't even think 5 watts. So that's good. That's really good. We're losing almost nothing in the mod. So that's pretty much all I have for you guys in this video. If you want to read up more, I'm going to link this video in the series versus parallel write-up. I'm going to link it in the battery sag write-up. Still don't know what I'm going to say in the battery sag write-up yet, other than just typing out what I said in this video. But if you want to read more, check out some of the files in the group, and it's going to help you understand this better and better. And this is all Ohm's law. Everything I've done here is the Ohm's law wheel, aside from battery data sheet, making a few assumptions about the resistance in your mod. And if you think these values are wrong, then make your own model with the values you think are correct, run the numbers, and get the results that are going to be correct for you. And that's fine. You know, this is, I'm showing you the math, I'm showing you how it works. This is one one example that I think is realistic. Check it out, guys, and all you box modders, read the fucking pen post. All you YouTubers, keep hating, and have a good day.